All right, everyone. This is the screencast for natural selection and evolution. So we'll start off with the definition of evolution. Evolution is the process of biological change by which descendants come to differ from their ancestors. So what this means is that we right now are completely different in some biological way to our ancestors. So we over time adapted or changed to what nature um, put upon us, whether it was a change in food selection or predator and prey relationships. At some point in time, we changed and we adapted to the situation, to the environment, and became who we are right now. And it will continue to happen for many years to come. Okay. Species is a group of organisms so similar to one another that they can reproduce and have fertile offspring. So, what that means is that a human being from the United States could mate with a human being from Japan, and they could have a baby, and that baby would later on be able to have offspring, have their own babies. That means that we're the same species, okay? You could have different breeds of dogs. For instance, you could have a Pomeranian who breeds with a Husky. That mix will have a baby, and that baby will eventually be able to breed again, and they're fertile. That makes them the same species. Same thing with Florida panthers and the mountain lions. When Florida panthers numbers were really, really low, we started breeding them with mountain lions, so that way we could bring the numbers of the Florida panthers up. They are very, very similar, so it's a hybrid mix, but they're the same species. On the other hand, okay, lions and tigers are not the same species. Yes, we have mated lions and tigers to make a liger. They do exist, but that liger is infertile. We cannot have two ligers come together naturally and create offspring. So that is one way that we could tell that the lions and the tigers are not the same species. Same thing goes with donkeys and horses. When you mix the two of them together, you get a mule, and we've been doing this for many years. Mules have been used for very, very many years. Mules cannot reproduce offspring because horses and donkeys are considered completely different species. Now, throughout scientific history, we have come up with different theories as to how the earth changes and how natural selection takes place in evolution. And one of those theories is catastrophism. Okay? Catastrophism is a theory that states that natural disasters like floods and volcanic eruptions have happened often during Earth's long history, and that they're the reason why animals became extinct over time. So a prime example would be the dinosaurs. We have very many theories as to how dinosaurs became extinct. One of them is the fact that there was not enough oxygen, not enough food anymore because they were so large. But the example of catastrophism would be the theory that a meteorite struck the Earth and destroyed the dinosaurs, and eventually we went into a nuclear winter and had our ice age. So that would be an example of catastrophism. And we figure out these theories by looking at fossils. And fossils are traces of organisms that existed in the past. So we look at these organisms that are embedded in rock or in shells and things like that, and we carbon date them, and we figure out when did this happen, when did this occur. And not just for the catastrophism theory, but for very many theories. Another theory is gradualism, which is the theory that changes in landforms resulted from slow changes over a long period of time. And a prime example of gradualism would be the Hawaiian Islands. The Hawaiian Islands were developed out of volcanoes that were under the surface of the ocean. Now, when hot magma hits the cold temperatures of the deep abyss of the ocean, it's very cold, so it solidifies and it hardens. So eventually you end up with these eruptions that keep continuing to happen over and over and over again, and they eventually broke the surface of the ocean, creating the Hawaiian Islands. The Hawaiian Islands then go through primary succession, which is when a landmass has never been inhabited or lived on before, and slowly goes through a process. It takes hundreds of years to where it ends up being from just plain rock to the big, luscious, beautiful waterfalls and green trees that we know when we think of Hawaii or when we see pictures of Hawaii. So that took over a very long period of time for that to take place. Volcanoes just don't erupt and create islands. Another theory that we have is called uniformitarianism. It's a theory that proposes that all the geological processes, so all the stuff that's going on with continental plates and volcanoes and hurricanes and things like that, today are the keys to telling us what happened in the past. So that's another theory that we have. Darwin, as you guys know, is the father of evolution, and he also proposed the theory of natural selection, and that's why we're going to talk about him a little bit. Charles Darwin traveled to South America and the Pacific Islands where he started his research. Okay, he was greatly influenced by the theory of gradualism. He strongly believed that over a long period of time is when these changes would start to take place, whether in animals or in land formations and things like that. So while he was traveling through South America and the Pacific Islands, he started to notice variations between similar species, and this is where we get the Darwin's finches. Darwin's most famous journal entries are always about his finches that he found on the islands. And he noticed that they all had variations on the islands. Variations, by definition, are the differences in the physical traits of an individual from those of other individuals in the group to which it belongs. So pretty much to break that down is that you could have the same species, but literally small changes in each one. A good example is human beings. We're all the same species, but we come in all shapes and sizes and colors. Those are all variations. Now you can have what's called an interspecific variation, which is between two different species. So, for instance, a killer whale and a blue whale. All right, they're both whales, but they're different species. Killer whale is black and white, and a blue whale is large and has a darker color. You can have an intraspecific variation, which is a variation that's within the same species. So, using the dog example, okay, there's a breed of dog called a Jack Russell, and you can have a short-haired Jack Russell, or you can have a long-haired Jack Russell, and that's just a variation within the same species of dog. Okay, the only difference is that the short hair has shorter hair than the long hair. The long hair has a longer hair to it, and it's more wiry, but they're still the same species. They just have a slight variation. And so with Darwin's finches, he's noticed this. And if you can see on the left, those finches have a shorter but much larger sized beak. They're wider. And it's because they create more force. So these finches needed these beaks because their food supply consisted of having to break through hard things like shells and nuts to be able to get to the food that they needed. So they had to have these larger beaks with stronger bite force that could get them through. Now the finches on the right, you can see, have a longer beak, and that's because they were going into the ground and into trees to get their food. So you didn't really need to have a short, strong beak. You needed to have a longer, thinner one to get through the soil and to get into more depth to be able to reach their food. So that's the variation there. And as you'll see on the next slide here, on the same island, present today, we have two different tortoises, and they live on the exact same island. They're just in two different areas. And so you have the dome tortoise here on the top, which you can see has much smaller limbs than the tortoise on the bottom, called the saddleback tortoise. The dome tortoise, its food supply is over by the ocean, so most of their food is coming off the ground or coming out of the ocean in an intertidal zone where they could go ahead and grab their food. So they don't need to have long limbs to get the food that they need or the nutrients that they need. Whereas a saddleback tortoise on the bottom here, his food supply is higher up. It's with vegetation that is much higher, so it had to slowly adapt and have this variation over time to be able to reach its food. Otherwise, its species would end up not making it. Plain and simple. That's food is one of the biggest stressors that nature could put on us that has caused most of evolution's changes over time. And you'll see that even with adaptation with jaguars. There were jaguars that used to have smaller jaws, and while everything that was furry and on four legs was running around, it was much easier to bite into those things and they could eat them. But once they ran out of that as a food supply, the only thing left was small turtles and things like that that have hard shells on the outside. So there were already some stressors in place that some jaguars were born very little with strong jaws and much larger teeth, and they were kind of seen as the outcast. So no one really wanted to mate with them. But see, then they're the ones who have the bite power to get through the shells, and they end up being the ones who end up surviving. So they can go ahead and breed, and then all of their offspring come out with large jaws that can break through the shells and they can survive. And that's one way of seeing survival of the fittest, because not necessarily that they were stronger or faster, but that their genetics gave them a trait that was fit for the environment that they were in. So that's survival of the fittest, and that's an adaptation and a variation just in between jaguars, or in between the two tortoises that we see here on this slide. So again, adaptation is a feature that allows an organism to better survive in its environment. And Darwin noticed this mainly with the finches, but with other organisms as well, and that was documented in his journals over time. And we can also see these adaptations that nature gave us just looking at fossils. The top picture here is a glyptodon and an armadillo. The glyptodon is the ancestor, obviously, and the armadillo is what we have present day. But we can see that the glyptodon on the top was much larger than an armadillo was. Most of the things that are ancestral to what we have today were very, very, very large. And that's because at the time they had an abundance of food. But again, like I said, food seems to be the biggest stressor that nature puts on an animal that causes them to adapt. So in the situation of the glyptodon and megalodon here on the bottom is that food supply ends up becoming scarce. So evolution says, okay, well, we'll make you smaller. You'll need less food and you can adapt to your environment that way. The glyptodon had a large, hard shell. They used to be hunted so that way they could be taken away from that hard shell because it was good for protection. But it was also very slow. But at the time, it didn't have any predators that it really needed to run away that fast from, that the shell couldn't protect it from. Whereas now an armadillo is much smaller than the glyptodon is, and so there are much larger things that could potentially hurt the armadillo. So an armadillo doesn't have a rigid shell on the outside. If you see, it has ridges on it, and that's because those ridges will eventually let it flex into a small ball, and it can roll itself out of danger if it needs to, or it can ball itself up and keep itself protected that way. Does it make it more vulnerable in a sense? Yes, because it's flexible, so at some point that tissue has to be able to bend and it could be penetrable, but it's suitable for its environment right now. On the bottom we see Megalodon, and Megalodon, as you can tell, is rather large. Okay, on the bottom left you see a modern day great white shark in comparison to Megalodon. And a great white shark now, most of them are between 16 to 20 feet. So looking at this, 16 to 20 feet, this great white shark is about half the size of a megalodon. So we're saying here that megalodon could possibly be 40 feet or a few, even a few feet greater than that on a larger scale. When you look to the right, you'll see a scuba diver. That scuba diver, if you were to actually scale it and move it up to megalodon's mouth, is about the size the distance from megalodon's nose at the tip to the back of his mouth. So easily a scuba diver could be sucked in there and megalodon wouldn't even feel it. Okay, we're very, very minuscule compared to him. Megalodon had teeth that were about 7 inches long. So if you imagine 7 inches, that's a pretty large blade if you were to think about in terms of weapons. I mean, his teeth going through you would essentially be almost like having a dagger go through